going heavy with IPv6. As far as the United States goes, as far as the government goes, they're not mandating, of course, anything for businesses and stuff. But one of the things that they are saying is, and that this started back in 2020. Boy, it's been 4 years, almost 4 years ago. This memorandum came out 4 years ago from the Office of Management and Budget to basically all agencies, head of all agencies. Let me just kind of read a little bit about this. But it talks about here, it says, the global demand for IP addresses has grown exponentially with an ever increasing number of users, et cetera, et cetera, et cetera. Over time, numerous technical and economic stopgap measures have been developed in an attempt to extend the usable life of IPv4. But all these measures add costs and complexity to network infrastructure and raise significant technical and economic barriers to innovation. It is widely recognized that full transition IPv6 is the only viable option to ensure future growth and innovation in the internet. Okay. So they've been moving forward on this, and I've been involved a little bit as far as some of the agencies that I've given some presentations and stuff too. But I know that it's something that is moving ahead slowly but surely. Okay, some other things that are happening. What's the, can you buy IPv4 addresses? Yes, and the cost has actually been going up. You can actually get IPv4 addresses, blocks of IPv4 addresses on auction blocks. You can either do an auction or you can just buy outright. And depending upon which region you're in, which RIR you're in, it is something. Now, what's kind of interesting about this is I was just reading a blog about this, and it's kind of, it can be doing this as an investment. Is there a, are you going to recoup your investment in this later on? And, so there was just an interesting article saying basically, these are going to become less valuable over time, these addresses. So, as organizations begin to transition to IPv6, they're going to see that they're not necessarily painting themselves in a corner, needing more IPv4 addresses. This was announced back about a year and a half ago, where Amazon Web Services said, hey, we're going to have to start charging for the use of public IPv4 addresses. Basically, they need to recoup their own costs in maintaining IPv4 and their costs of maintaining the public IPv4 address space and what they have to do that. So they don't charge for IPv6. So where are we? Well, I just want to mention this, this guy here, Jeff Houston, very well known at AppNet. He's actually does a lot of, what I showed you, the weekly IPv4 statistics. He's kind of the one that kind of does all that. He's the one that does this famous BGP table. I don't know if I can, it wasn't there last time I was looking for it, about showing the total number of IPv4 and IPv6 addresses being used out in the internet, the global routing internet table, a full internet routing table. So anyway, he's very much involved in a lot of what's going on with the management of IP and IPv4, IPv6. A matter of fact, at Nanog, I'm waiting for them hopefully to post it on a video, and I'll share that with you. He just gave the keynote on whatever happened to IPv6. This just was on, what day is this? This was yesterday. He gave the keynote, I believe, at Nanog conference. But he wrote an interesting blog. I'll put this on, if I haven't done so already, I'll definitely put it on, no, I did put it on Canvas, so it's there for you. But he talks about the transition IPv6. It's a long blog, but in short, what he talks about is one of the reasons why it's taking so long is that there has been no widespread sense of urgency. And that actually leads to more of a kind of a, we can put it off till tomorrow. And like I said, I'm not an evangelist for IPv6. I'm not pushing it. You got to go to IPv6. Okay. I'm just a realist. I know that it's an eventual thing and something that we, as a network professional, something, I need to be aware of and be comfortable with, like I am with, hopefully, with other technologies. So he says one of the things is the factors, the high cost of running dual stack environments, IPv4 and IPv6 without immediate benefits. The idea of adding IPv6, if you don't have to do it and there's not an immediate benefit, either cost or performance, people are putting it off. That's why a lot of enterprises, especially in the United States, have been putting it off. And then, of course, there's things like network address translation and carrier grade NAT, where we're just using NAT to use a single public IPv4 address to represent hundreds, even thousands of private IPv4 addresses. Also, there's something that has happened recently with the whole, with TLS and something called server name indication feature. But basically what this allows is a single server with one IP address to host multiple services using different domain names. So, we're, this is what happens a lot in the cloud, where you're not just going to, when you go to Amazon.com, you're not necessarily going to a single IP address that belongs just to Amazon. Okay? You're going to a server with a public IP address that behind that public IP address is hosting multiple services, multiple websites. There's also more with content delivery networks and many other things that has just made how we access the internet, what we use it for, made it a little bit more, I want to say, kind of where we have, it hasn't been a one-to-one, where we don't need a specific IP address anymore. It's making the NAT and some other things with SNI. We're able to get away with representing services with fewer IP addresses. But he suggests that, transition to fully IPv6, dual stack is going to continue for a while. So we got to understand that. It's going to be a transition. We're going to be running both. A few years ago, it was looked at as, we don't want to run both because this is why the federal government and China, they're saying it's too costly. To do both. And that's true. You do have to do everything twice, IPv4 and IPv6. But says, eventually IPv4 will be phased out. And as businesses begin to realize, that IPv4 is less sustainable. Yeah, Pamela.
Thanks, Rick. I was just wondering, in terms of running both, when you said it's going to be more costly, have they already worked out all the details in terms of streamlining the communication, and that's where the costs come in? And have they thought that, I'm guessing they've thought it through, but I'm just wondering the possible obstacles in terms of the communication.
Well, yeah, really the costs that they're talking about are things like the, just when you configure all your devices, okay, you got to configure everything for both. You got to test for both. You got to verify for both. So, and, it just adds more complexity because you've got to, it's not that IPv4 and IPv6 are entirely different in every way. They're not. Okay. But when you do an access control list of what you're going to permit and deny outside your network, you gotta do it for an IPv4 prefix. You gotta do it for IPv6 prefix. Um, when you're doing your routing, you've got to route both for the IPv4 packets and the IPv6 packets. And, for smaller networks, it's probably not as big of a deal, although that also means you have a smaller IT staff, and maybe less knowledgeable in the world of IPv6. So it can also, that's can be a big deal in that respect.
Thank you.
So it's just that as far as the communications, as far as forwarding packets, it really doesn't make that much of a difference. It's mostly the cost of maintaining this. And then when there is an issue, where does the issue lie? So it just makes things a little bit more complicated. Does that help?
Yeah, immensely. Thank you.
You're welcome. Okay, so back to learning a little bit about IPv6. Two questions, and by the way, we're going to talk about how we got to IPv6 in a moment, because that, I think, something important for somebody that's knowledgeable in IPv6 to also understand. So, two questions you may be asking yourself. One, exactly how many addresses are there in IPv6? So let's get that out of the way. And the other thing let's get out of the way is what happened to IP version 5. So let's get there. Let's get IP version 5 out of the way. IPv5 was actually a group of experimental protocols that was developed to help with things like streaming video, known as Internet Stream Protocol. It was never a separate protocol by itself as far as the network layer IP. What they did was they said anytime the streaming protocol is being carried as data in the IP packet, the version number of IP will change to 5. Well, because that kind of became a standard, although it was never implemented, that took version 5. And of course, once it's done in stone. So there's that's what happened to IP version 5. So next up would be IP version 6. So how many addresses are in IPv6? Well, if we look at IPv4, we have 4.29 billion addresses. Okay. In IPv6, that's a 34-bit address. What we mean by that is 34 zeros to 34 ones. We have a total combination, different unique combinations of zeros and ones of 32 bits, 4.29 billion. Now, just like every time we add a digit in base 10, we have 10 times what the previous positional number was. Like if I go from the ones position to the tens position, now I have tens. The next position is hundreds, thousands, etc. In base 2, every position every time we increase by another position, another digit, we're actually doubling the number of possibilities. So going from 32 bits to 128 bits does not give you 4 times the number of addresses. Every time you've added a bit, you've doubled the number of possibilities you have. So 128 bits, this gives you 340 undecillion addresses. Okay. So what is that? Okay. What exactly does 340 undecillion? How big is that number? Okay. And now these aren't analogies I came up with, and I haven't tested any of them. Okay. But there's many of these out there. Let me share a couple with you. If you had a job that paid, I am recording, right? Okay. This fear I have, already this week I was teaching a class and forgot to do the recording. All right. If you had a job that paid $390 trillion per hour, You would have to work every hour of the day, every day of the week, every day of the year, and to earn just one, to earn just, let's see, for just a little less than 100, you have to do this for 100 quadrillion years to earn 340 undecillion dollars. Excuse me. What if you had a 300, something they paid you in 340 undecillion $1 bills? Well, a single dollar bill weighs about 1 gram. If you had 340 undecillion $1 bills, it would weigh about 50 billion times more than the Earth, which would form a mass, form a black hole about 180,000 times more massive than the sun. I don't know. I didn't test these. These are just things that are out there. So, anyway, give you an idea that it's a lot. It's a lot. So, I'm at UCSC today, not at Cabrillo, and so I don't have an IPv6 connection here. But I wanted to show you that this is showing IPv4, private IPv4 natted to a public IPv4 space. So let me just show you that, and I'll show you. This is, let's see, where am I doing? This is from Cabrillo, actually. Oops, that's not what I want. All right, just share a little bit with what I'm showing here. I wrote a little Python program that I'll share with where you can get this if you're interested. That asks you what version of IP you're running first or what you want to see. You can go to any Amazon, boy, excuse me, any website you want. And it will give you your private IPv4 address, so that's me at school. Then it will show you your public IPv4 address. It's the one that belongs to Cabrillo. It also shows you the DNS server as well. All right. What this shows here is the packet leaving my computer. It left my computer with this IPv4 address, and when it reached Cabrillo's router, excuse me, it was translated to this IP address. This is the public IPv4 address that at the time I was using for Amazon, or that DNS gave me for Amazon. When the package came back from Amazon, it came back going to, well, first of all, from the source address of Amazon, its public address. It was going back to the public address of Cabrillo, this address right here. Okay. And then when it reached the router, it got translated back to my private IPv4 address. So that's what that is showing right there. Okay. This is similar, but this time from my same computer, I chose IPv6, same website. Here it's telling me this is what your IPv6 address is. Now it looks ugly, but it really isn't. We'll talk more about this on Tuesday. This is Cabrillo network. This is our subnet. And then this here is my interface or host portion of the address. So as you can see, when it left my computer, it left with that address, no translation. Went to Amazon. When it came back from Amazon, yes, Amazon uses IPv6, it came back directly to my IPv6 address, no translation. Okay. All right. So why did it choose what if I didn't choose? So if I just went to www.amazon.com, which one would it choose? Well, there's an RFC called Happy Eyeballs. What Happy Eyeballs is it's an RFC written by Andrew Yurchenko, the one that did this nice little NAT video that I showed last time. Excuse me. But basically it says that the operating system will prefer IPv6 over IPv4. So if the website can be reached over IPv6, it will choose that. All right. By the way, those videos, along with the Python code, is available on YouTube. So if you go to my YouTube channel and you click here, it'll give you my GitHub repository. The only thing that you could use my code, do what you want with it, make it better. The only thing I ask you to do is that you can't do with my code is don't criticize Rick's coding ability. Tongue in cheek there, but really not really. It's so when I write my code, I'm not the greatest programmer, but I enjoy doing it. I used to be a programmer that was in another life. But a lot of times when I write these programs, it starts out as something, I'm just going to do just this. And then I start adding more and more and more. No, I want to do this. I want to do this. Before I know it, it's not how I would have started out writing the code, because now I've got things all over the place. Call it spaghetti code in the old days. And it's like, oh, well, it works. So anyway, that's my code. All right. Let me pause just for a second, clear my throat.
Recording stopped. Recording in progress.
Okay. Okay, of course I have no water. That's all right. So let's get into the story of the day. How did IPv6? We stopped at 9:30 last week, huh? No, we go till 10 o'clock. Sorry, I don't know why I thought I just realized it's 9 o'clock here, and okay, till 10 o'clock. So we're doing good. Sorry about ending early on Tuesday. I don't know why I realized that now. I looked at the time. Okay, too many tangents here with Rick this morning. Now, how did IPv6 become the next IP, or even the next network layer protocol? You're like, well, what? Yeah, there was no IPv5. They chose IPv6, right? And IP was going to be, just a newer version. Well, wasn't that simple. So let's again go back in time, because this helps us understand where we are today and how we, why we're in this situation of IPv4, IPv6. So the Internet Engineering Task Force, which came under control of the Internet Activities Board, now called the Internet Architecture Board, okay? They're the ones that are focused on protocol development. And they, of course, TCP/IP was what they were. That was their, the IETF and IAB. That was, back from the days of ARPANET. It started from NCP going into TCP/IP. Okay, so, but we'll see in a moment. There was other protocol suites out there. But let's look at 1992 and let's look at who was in the IETF. The IETF, and I mentioned some of these companies and organizations because they were some of the first early adopters of IPv4 addressing. Okay, but they include everything from government agencies, network service providers, internet organizations, etc. Let's look at some of these. So NSF played a crucial role. They were funding a lot of the internet for quite some time. Department of Defense, well, kind of all started there with DARPA and ARPANET, the Department of Defense. So they were part of IETF. NASA, which was also doing a lot of collaboration with universities and research institutions and doing a lot of stuff with wanting to do a lot of testing of internet type of technologies. Universities such as Stanford and MIT. Stanford is where Vint Cerf and Bob Kahn were affiliated with. There's also, I should mention, UCLA was also one of the big ones. USC, John Postel, down there at USC, actually part of their Information Sciences Institute. I believe that was down in Marina del Rey. I used to see that all the time when I went to college. Managed a great deal of what was happening with IP addresses and other things later on as well. Private companies, AT&T and IBM, I mentioned them. They were the big computer company, communications company of the day. But they weren't early supporters or believers in this whole packet switching idea. Matter of fact, they thought it wasn't going to work. But we don't really recognize how big AT&T and IBM were today. Today, it's hard to see that how dominant they were back then, and they were dominant. Okay, in their respective fields. Cisco Systems was already beginning to build some routers and networking equipment. They were heavily involved. Sun Microsystems, which was known for what they were doing with Unix. Some networking companies, I mentioned them earlier, Beranek and Newman, I believe is how you pronounce that. BBN. Big role in the early days of the ARPANET and the internet. They're the ones that built the first router, information message processor, which was if I remember correctly, I think it was a Honeywell 516 mini computer. And delivered the first one to UCLA. And those hooks on the top were so a helicopter could actually lift up the thing. Yeah. The size of a refrigerator. Xerox PARC, Palo Alto Research Center, they were doing, they had people like Bob Metcalf that were doing the Ethernet stuff, but they were also contributing to the side of the internet as well. Some early network service providers, now we think of them as internet service providers, but no longer around, UUNet and MCI. RIPE NCC and APNIC were just beginning to get formed, although they were not fully operational. They were involved in IETF as well. So here we are. We have TCP/IP protocol suite over here with the IAB, IETF, and all that good stuff happening over here. But there's other protocol suites too, and some that are kind of long forgotten. But there were some others. There was actually IBM was trying to develop their own protocol suite because they were really trying to push the way that they did things, which was, and kind of what was most beneficial to kind of their way of thinking about computing. But it really came down to this. It really came down to the ISO, International Organization of Standardization. That's this is not a acronym. It's actually ISO, meaning equal in Greek. Which was ISO had been around since World War II, and they were all about standards, global standards. If you've been involved with any kind of international standards as far as business, quality assurance, transportation, health, you name it, there's an ISO standard. So they're all about standards. So they were developing their own protocol suite. They're the ones that came up with the OSI reference model, okay? That we still use today when we talk about TCP/IP. So we had these two happening. Now, remember the year was 1990. The ARPANET, and now the early internet with the adoption of TCP/IP as far as how the ARPANET transitioning to TCP/IP, very U.S.-centric, okay? Now remember, there's no Amazon, Netscape, Yahoo, no web browsers. Web browsers just started to come into play about 1993, 1994. But Americans were the predominant users of internetworking in general, and definitely of the ARPANET. The internet population was small. It was, only about 3 million users. And most popular application was text-based email. There are no images, video, voice, or any of that sort of thing. Okay. All right. So here we are. We're ISO versus IETF. Okay. IPv4 only been around for about 9 years. Okay. Was this going to be just another protocol suite that came and went, another experiment that was, and be replaced with something else, or was it going to continue? OSI was advancing, really pushing their ISO was really pushing their OSI protocol suite. It was not U.S. centric. It was pretty much European centric. And it was in contention, and they kind of thought that they were designing the protocol suite of the internet. They'd already been sanctioned by numerous governments as yes, you've got our backing. This is where we want to go with all this. Even the U.S. government said, yes, we want to look at transitioning to the OSI standard. Yeah. So despite our own government endorsement, there was this kind of competition happening between these two protocol suites. So 1992, this is when the Internet Activities Board, they met in Kobe, Japan. They realized this is where they're going to discuss IPv4 address exhaustion and what are we going to do about it. Okay. The IETF reports to the IESG, Internet Engineering Steering Group, and they report to the IAB. The IESG wanted to do really IETF wanted to do a new version of IP. That's what they said. Let's do a new version of IP. That's what we're familiar with. That's what we've got working well. But the Internet Activities Board, without referring to the IETF, which is normal and customary, that this was the people that were doing it. The IETF were the people that, hey, they knew their stuff. They had been working hard. They're the worker bees. Okay. They said, okay, what we're going to do is we're going to propose a new layer 3 protocol. And what they proposed was CLNP from the protocol suite. Okay. But they said, what we'll do? Just going to use their CLNP network layer protocol, and we'll run TCP and UDP and the applications on top of it. So we'll replace IP with CLNP. It has a 160-bit address. Okay, and CLNP already existed. Okay, and like I said, we're going to use on top of that TCP and UDP. Okay, so but as far as the new network layer protocol, we're going with CLNP. They actually dubbed it IP version 7. They erroneously skipped version 6 for some reason. They knew their 5 was taken. I don't know why they came up with 7. All right. Well, this did not make the IETF happy. Made them very angry. They expressed, on the mailing list, they expressed outrage. Okay, here's some of the statements from the mailing list. You can still see these today on the mailing list. Okay, but basically they just, livid, just livid, for several reasons. So first of all, they thought that ISO was kind of a big bureaucracy. IETF had a very streamlined approach to drafting protocols, getting them tested, verified, and if they met consensus, said running code, consensus and running code, then and was something that the working group and the IETF recommended become a standard. ISO, everything was very bureaucratic. So they're worried that first of all, they're gonna lose control over what they're doing. As, you know, it's like reporting, getting bought out by another company and who you're reporting to. Okay, so they're really worried about that. They said no. You know, let's stick with IP. We can make IP better, and it more in lines with what we're doing with TCP and UDP and that sort of thing. So so after all of this backlash from the IETF, and there was a lot, not just from the IETF, but anybody working with TCP IP, there was a huge backlash. The IESG recommended to the IAB, Internet Activities Board, and they agreed that, okay, let's start over. Let's look at other alternatives. So Vince Cerf, who was actually running the IAB at the time, he he was trying to be more diplomatic and global about including ISO, because really ARPANET, now the early internet, was very US centric, and he realized for this to really grow, we needed to be a global community. But got the message. He withdrew the proposal to have CLNP be the new protocol, and said, okay, let's do this. Let's have a process. And so in 1993, RFC 1550 was a RFC that said a call for white papers, next generation of IP. What, hey, submit what you think you want it to be. Okay. And here are some of the key members of that selection committee, okay, along with some of these others as well. So this is who was going to select the next version of IP, or would it be CLNP? I think we already know who won, right? Okay, so these are the finalists. Okay, so so where you see IPv6 is right here. They're going to have a 64-bit address. Okay, there you can see Steve Deering, Bob Hinden, Christian Wheatma, very well known in this industry. It was called SIP, Simple Internet Protocol Plus. This is what would be the next. This is what they called their proposal. There was also something called TUBA, TCP and UDP with bigger addresses. But this was basically CLNP and we saw BBN and DEC. DEC was a big fan of ISO. And then over here was kind of a combination of a bunch of things, and they weren't really seriously all looked at. So it really came down to these two. And who won? Well, first of all, the catnip proposal. They were just angry at, the IETF. Let me just read this. This is in their proposal. The argument that the IETF need not or should not follow existing ISO standards will not hold. Hey, ISO, that's the global standards. We should all be, so it's kind of like, you don't have to, that's how big ISO was as far as viewed as having global international standards. The ISO is the legal standards organization for the planet. Every other industry, transportation, everybody, healthcare, develops and follows ISO standards. But yes, you should too. ISO convergence is both necessary and sufficient to gain international acceptance and deployment of the next generation of IP. Wow. That's how big of a battle this was. Okay. The committee announced that they were going to go with SIP, go with an IP based. But an IETF would preserve control over the standard, not ISO. Okay, so yes, and that has continued since. The whole TCP IP protocol suite is controlled, the standards is controlled by the IETF. They did announce that it would be called IP version 6 since 5 was already taken, and they're going to change it from a 60-bit address to a 128-bit address. So that's the story. This is Bob Hinden talking about it at a conference. If you want to, it's a long conference. He talks about many different things, but there's the link of that. I'll put that on my Canvas page. Protocol Politics. This is a book that talks a lot about the politics of what happened during that period and who was involved and all that kind of thing. Excellent book here, Where Wizards Stay Up Late, The Origins of the Internet. Really doesn't talk so much about IP, but really how all this started from day one. This is I believe this is the game from BBN and the first IMP. But talks a lot about people like John Postel and others. And a lot of the people that were the Licklider at, where was he at? My mind this morning. But just a lot of the people that were involved in the early days. And it's fascinating because we take it for granted how easy this is today. You just don't have to do anything and you're connected. The idea of getting computer A to talk to computer B over a wire, let alone many computers in the same group, like a local area network, or how to get a computer from one network to talk to a computer somewhere far away in another. How are we going to do this? And there are a lot of competing ideas on how to do this over the years, and still is, which is a good thing. So anyway, great book. Talk a little bit about IPv6 today. Okay, all major operating system, end device operating systems supported by default. This is my home. Yep, that's actually a picture of my house right there. My house, my IPv6 address at home. I'm going to be talking a lot more about how we look at all this address stuff. This is me at home. Let's see, 642. Yeah. I have my own IPv6 network. We'll talk more about reading all this. My phone. So this is because Comcast is my internet provider. Yes, Verizon's my cell phone provider. Mobile, big adopter of IPv6. They've had no choice with all the mobile devices. This is showing from, where am I? I'm at school here. This is at Cabrillo. This is another Python program I wrote and that I ran that shows what at any given time. So I was just like what I'm doing here. I got a bunch of tabs open, just my normal work business. What's connected versus IPv4 and what's connected via IPv6. And when I'm on an IPv6 network at school, which is my office, we have IPv6 connectivity, or at home. I'll show you all this stuff from my home computer as well. I have Comcast as my ISP. I did nothing to say, hey, I want IPv6. I'm a normal user as far as what I'm getting as far as IPv6 from them and what is being sent IPv6. Okay, so I'm just, a normal user that knows nothing about IP and doesn't need to know anything. I just plug in my devices. And most of the stuff that runs between my house and whatever I'm doing is over IPv6. Yep. All right. So, I think in my video, I got both of these on YouTube video, and I talk about what you're seeing here. Okay. So these are, most of what we connect to is at some kind of cloud provider or a content delivery network. All right. We'll take a quick 5-minute break here. But I just want to make sure. Yeah, let's see here. I'll make sure those Python programs are up here as well. So yeah, let's take a 5 minute break. And then I will go ahead and add some more links and videos and try and get them up there now for you in case you want to look at that. All right. How's everybody doing?
Okay.
Everybody doing okay?
Recording stopped.
I hope you're finding this just useful. I'm giving it to you from my perspective. So anyway, we'll talk more about all this stuff. Let's take a 5 minute break.
Rick?
Yes, Roger.
There's two of me on Zoom because I'm playing around with I'm on my computer and my iPhone connected to my TV mirrored.
Okay,
So
no problem.
I'm,
Yeah, I saw you come in again.
I'm
Not a
just
problem.
experimenting.
Yeah, no problem. You can have 2 or 3 of you, 4 of you, I'm okay with it. Right. Started.
Recording in progress.
All right, let's continue here. So I was showing you couple little programs. Another one that shows you whether what I'm currently connected to is IPv4 or IPv6. That I so that part, and I'll just put the playlist up there. It's another playlist. So I have a playlist using Python to examine network connections. And you'll see it right here using netstat to list all connections. So that's what I'm using, is actually something called netstat. And then I'm using Python to display everything in a certain format that we're looking at. But that's that program here. I'll put that playlist there. And once again, if you go click on these links, you may see in your browser, I know what causes it, but whether, I know with me, it's Safari, Chrome, and Firefox all do the same thing. So when you click on a link, you'll see some kind of message, looks like it doesn't come up, just click right at the top here, and that'll take you to the playlist. All right, you know what, I want to show you one more. Love this. So since we've talked about the transition to IPv4 to IPv6, and I've got to share my sound with you here, and we'll talk a little bit about the protocol itself. Share a computer sound. All right. This is the one I want to show. So what this is showing is, here's the date up here, 2004. Is when IANA runs out of IPv4 addresses. More in 2014. That's when we reached we start to see more regional internet registries begin. probably didn't hear the sound. I was running it off the run. Oh, you didn't hear the sound, did you? There's good sound there, good music. Ah,
I
that's
could
right.
hear
You
it.
could hear it. Oh, you could hear it. Probably
Yeah.
was hearing it from my computer. Okay, good, good. So sharing my sound. Good. Oh, the music was like the best part. All right. Okay, here, let's go up here. Okay, comparing a little bit of the IPv4, IPv6 headers. Okay, so when we display IPv6, we usually display it as, we're 64 bits, kind of a word wrap. In most protocols, the TCP/IP protocol suite is always shown as 32, as 32 bits, another 32, 32. Excuse me. In IPv6, we do 64. Okay, these are some of the similar fields we have in both. Some have been renamed, okay, and resized. But there are several differences. First of all, IPv6, you may notice it's actually a simpler header. Okay, there's actually fewer fields to it. It's also fixed at 40 bytes. Talk a little bit more about that in a moment. We doesn't have options in padding. It does something slightly different for what this was intended to do. So first of all, the version, they both have a version field, okay? All right, that's good. And yes, I think you can guess this has a 4, this has a 6 in binary. It's all in bits. Version 5, we talked about that already. No, it was a streaming protocol. Okay, so internet header link. So this is a field that does not exist in IPv6. It exists in IPv4. What this field does in IPv4 is that it says how many 32-bit words, think of this, or 30, well, just think of 32-bit chunks. We call these a word, but 32-bit chunks are there. Why? Because in IPv4, they have this idea of options that very rarely gets used. But so you could have more 32 bits, could be longer than just the 5 times 32 bits. That's the IPv4 header. And by the way, it has to end on 32 bits. So whatever number of bits you need to add to the options, it's got to end on a 32-bit boundary. And that's why there's some padding at the end. I think some 0 bits is what they use. IPv6, this is not needed because the header, it's one size. It's 40 bytes. And actually, it's not significant today, but it does say processing when figuring out, well, where's the next piece? Where's the data that follows this? Where's the next protocol that follows the IP header? Okay, we'll see that with IPv4, that has to be determined. So both IPv4 and IPv6 have something called, well, they call it total length in IPv4. Let's talk about what the total length is. So an IPv4 total length is the number of bytes of the IPv4 header plus any option. The number of bytes of the IPv4 header plus data. So what it is it's actually the IPv4 header plus the data. It's all of that. Okay. So, and by the way, that means if you want to find out how big the data is, you have to take the total length field, subtract it by the internet header length, and you get the size of the data. Well, IPv6, it's not that complicated. Okay, we already know the header is 40 bytes, so it just says, yeah, that's not going to change. So let me just tell you what the size of my payload is, how much data I have. So you actually have to calculate that in IPv4. In IPv6, it's given because the header length is fixed. All right. It does include any extension headers. We're not going to spend much time on this, but if there are something called extension headers that allow IPv6 for additional features, header features that aren't part of the standard IPv6 header. They decided to do that instead of options. That way, everything is at a fixed length. We're not going to worry about the extension headers. But the data, the payload length would include if it's just data and if there's any extension headers. Okay, they both have what's called type of service or traffic class. Okay, they both do the same thing. They just renamed it in IPv6 to traffic class. Okay, this is not required to be used in IPv6. I know the early RFCs of IPv6 says it was going to be required that you have to use this. You don't have to use it in IPv6. It's not mandated, but it's the same functionality. I'm not going to get into this in this class, but it's where the same thing that we'd see for type of service. It's the same thing here. We have IP precedence or the differentiated service code point, DSCP. I talk about this in my CIS 83 class. We talk about quality of service. But we're just going over kind of the similarities and differences here. Flow label, that's something that is unique to IPv6. It's being used, but there's no real use for it yet. It's being included, but there's no use. What does this do? This is a way that a source to a destination, if I've got a bunch of packets I'm sending you to two different users, I can identify it as two different flows. So all the packets from a certain web server to you over IPv6 will have the same flow label. Why? How can that be used? It can be used by routers along the way or your own routers internally to identify all the packets that belong to the same flow, the same stream of packets going from the source to the destination. So it's one of those things that could possibly be used for a future enhancement. Okay, one of the big differences in IPv4 and IPv6 is IPv4 uses something called fragmentation. Okay, and that's what all these fields here are about. And I'll talk about what fragmentation is in a moment. IPv6, there is no fields for fragmentation. Okay, so what does that mean? That means routers do not fragment packets if they're too big to go across the next hop link. What do we mean by that? Okay, so let's say PCA is sending a packet to PCB. It gets from PCA to router R1, R1 to router R2, the packet. Okay, of course it's encapsulated in some kind of data link frame. But this maximum transmission unit, whatever this link requires for MTU, is smaller than the actual packet. It's like somebody bringing I used to work at a hardware store in college, like a home improvement store. And people would buy a big box of something, okay, whatever it is. And then they say, oh, can you help me take it to my car? Sure. And then I get to the car, it's like, it's not going to fit in your car. It's not going to fit in your trunk. Okay, so that's what we have here. It's not going to fit. It's too big. So we didn't do this. But what happens is you have to take that data, break it up into separate, smaller packets, meaning the data is going to be smaller. Separate IPv4 headers, but with smaller data. Then that's called fragmentation. It makes its way all the way to the destination. These routers, they're not going to put it back together. They don't care. That's not their job. So it gets all the way back to the destination where it's their job to reassemble these fragments. Okay. In IPv6, there is no fragmentation. So the way IPv6 handles it is if a packet gets there with an MTU that's larger than the link, this router will drop the packet and send a message, an ICMPv6 message back to the source saying, hey, I had to drop your packet and because it's too big. It's actually a packet called packet too big message. So one of those rare times when somebody names something that makes sense, that we actually can understand. And it says you need to change the size of the packet to 1350. So tells the source says, yes, I'll remember that from now on, and sends all the packets to the destination and no assembly required. Okay. This is much more efficient with how things are handled today on today's links, and much more common. Okay, the next one is actually a field that just got renamed, called protocol field in IPv4. We just call it the next header field, like what's next? Okay, what am I carrying next in IPv6? Basically, it just indicates what's next. What am I carrying? Common values, here they are for TCP, UDP. It's just what's in the back of my truck. Okay, same thing as the protocol field in IPv4, just renamed in IPv6. The hop limit, time to live. So time to live is what we call it in IPv4. In my CIS 81 class, we're going to be getting to this here shortly. Okay, actually in the next week or two. I think next week we'll talk about Internet Control Message Protocol. But time to live field in called time to live in IPv4, called hop limit in IPv6. What happens is this: every time a router gets a packet, it decrements the time TTL or the hop limit by 1. This TTL or hop limit is set by the source, whoever created the packet, the source, the original source. Common values, it can be up to 255. Common values are 64 hops. The whole idea of this is that if we have something called a routing loop, we talk about this in my other classes, CIS 82, CIS 83, where one router is sending the packet to another router that might be sending it to a third router and then back to the original router. The packet is going around in a loop. And why does that happen? Either misconfiguration, or it's a temporary loop due to what we call convergence. There's a change in the topology of the network, and not all routers have seen that change. Or yes, it could be a misconfiguration issue, or just something that, I'll get into some other causes and solutions in my other classes. But anyway, you get the idea. If the router gets a packet, the time to live or hop limit is 1, decreases it to 0. It says, oh, you're going no further, and actually drops the packet. There is no such thing in Ethernet, by the way, okay? Which is something that was later thought of, should we have done that? We meaning not Rick, okay? They're much smarter than me. So it was just renamed to more accurately reflect the process. Okay, IPv4 has something called a checksum field. What that is used is to check the integrity of the packet, make sure, did anything get flipped? Did any bits get corrupted or dropped, or something happen along the way? That this isn't what was sent. This is not used in IPv6. And the reason why is because when they developed IPv6, says, look, why do we need to do this? TCP and UDP, who are going to hand the data off to, they already have this. And even ICMP has it. So why do, the data that we're carrying is going to do this again anyway. So it's not included in IPv6. Now, let me just mention, here we go. Here's TCP and UDP. My CIS 81 class, we have not talked about this yet, but we will. This is what's carried inside, encapsulated by IP. One's a reliable protocol, one's is for unreliable. Talk about that later. They both have something called a checksum. It is required in both IPv4 and IPv6 that for TCP to do the checksum, make sure nothing got changed. In IPv4, the checksum is optional. However, if UDP is carried in IPv6, it must be checked, validated, because there's no checksum in IPv6. But IPv6 said, look, you're both doing this. I don't need to be doing this. And also Ethernet has a frame check sequence. So we're checking things at multiple points. All right, let's get to this. Here it is, the IPv4. This is what we all know about the difference, right? The source and destination addresses. Okay, IPv4, 32 bits. IPv6, 128 bits. And some significant changes in the types of addresses that they are. We're going to be talking about that. We're excited about this on Tuesday. I talked about the options and padding in IPv4 a little bit. That's just used in case you want to add more features. There are some things that they rarely got used. Optional features to the IPv4 header, not used in IPv6. Okay. Again, I mentioned in IPv6, we use the extension header. I think showing that? No. We have something called an extension header. Okay, as far as Ethernet carrying IP packets, okay, in IPv4, we talked about this type field. Okay, I might say in IPv4, in my CIS 81 class. Ethernet has a ether type field. It says, what am I carrying? If this is an IPv4 packet, then it's 0800 hex. And I'll be showing you some of this in Wireshark and some other ways as well. In IPv, if this is IPv6 packet, then it's going to be 86DD in hex. Okay. And there's other things too, like ARP. Remember ARP from IPv4 would be 806 hex. And there's other things like spanning tree and things like that. So remember, with Ethernet, it really doesn't care about the data. All it says is, hey, it's just, you know, it's just whatever content I've got in the back of my truck. All I do is get it from one NIC card to another NIC card within my own local area network. That's what Ethernet does. Okay, yeah, so this is showing, it would be 0x0, well, 0x. That 0x, by the mean, that means hexadecimal. That means this is a hexadecimal value, 86DD. I'm not going to talk much about extension headers, but there are extension headers. So you can have multiple extension headers. But we're not going to spend much time on that. Okay, let me talk a little bit, introduce us to what we are going to talk about next week. And again, I've got videos here. There's the comparing IPv4 and IPv6. I'll always show you, mention the videos. If you really want the long story, long introduction, but I think what I'm doing now is even a better introduction to IPv6 and how we got there than this long introduction. 45 minutes, way too long for it to be talking about that in one video. We're going to start talking about IP address representation, how to actually how IPv6 addresses are represented, and the different types of IPv6 addresses. Okay. There's some stuff that I'm going to talk about in this class that is not part of my book or the videos, including multicast. Multicast is talked about here, but I'm going to talk about it in a little bit more detail and a little earlier on, because it plays a significant role how layer 2 and layer 3 multicast. And you're like, what is multicast, Rick? I will explain that. We will get there. All right. So other than that, how's everybody doing? You doing okay?
Yes, thank you.
You're welcome. And again, I just want to mention, this is how this is going to be. It's a seminar based. There's not any homework labs. I'll share with you everything I have. But if you're really looking for a class like that, then, you know, just to be, set everybody's expectations, then you probably want to drop this class, okay? Because this is going to be more Rick just explaining how all of this works and answering any questions that you may have and sharing some stuff about how it works. Okay, so it's not a class where we're going to have assessments and labs and stuff. I've done that. I just don't, it takes a lot of time, and it's better to do it on an in-person class. It's harder for me to do it over, you know, Packet Tracer unfortunately doesn't really support it, and NetLab doesn't really support with the way that we need to get everything set up to do it. So I hope this works for you. I understand if it doesn't, again, you know, just withdraw. No, don't, I understand, it doesn't hurt my feelings. If this has worked for you, look forward to having you the rest of the short semester. All right?
Okay.
All right, I wish everybody a good day. Hope everybody doing well, have a good weekend. I think it's gonna start getting cooler. So, all right, have a great day, everybody. Thanks.
Thanks, you too.
You too, thanks. Yeah, John, let me stop.
Hi, Rick. I noticed when you were showing